Last time we solved the wave equation for a plane wave in one dimension, that is psi equals a cos kx plus b sin kx, which can also be written in the form psi equals a times e to the power I kx, and we showed that this is an eigenfunction of the linear momentum operator in one dimension, that is minus ih cross d by dx, and we showed that minus ih cross d psi by dx is equal to h cross k psi, where the eigenvalues of linear momentum in one dimension are px equal to h cross k. This is the de Broglie relation, and where k is the wave vector which has the dimensions of inverse length. In 3 dimensions, we can generalize this to psi equals a e to the power I k dot r, where k and r are vectors. R equals I x plus j y plus k z. K is I k x plus j k y plus k k z, the 3 components of the wave vector. And so this is an eigenfunction of the linear momentum operator in 3 dimensions minus ih cross del, where del is I del del x plus j del del y plus k del del z. So we see that just as before, minus ih cross del operating on psi is equal to h cross k times psi, which is the linear momentum eigenvalue p times psi, where p is equal to h cross k. A free particle means that there is no potential acting upon the particle. That means that the potential energy V is equal to 0, and therefore the Hamiltonian or the total energy operator for the free particle is just the kinetic energy operator, T equals half mv squared or half p squared by m, where p is the linear momentum operator minus ih cross del. Therefore, the Schrödinger equation for a free particle in 3 dimensions takes the form h psi equals minus h cross squared by 2m times del squared psi, which is equal to E psi, which can also be written in terms of its components as minus h cross squared by 2m times del squared psi by del x squared plus del squared psi by del y squared plus del squared psi by del z squared. So the Schrödinger equation for a free particle takes the form h psi equals minus h cross squared by 2m times del squared psi equal to E psi. And we can show that its eigenfunctions are plane waves, that is psi equals a e to the power I k dot r. To show this, note that del psi is equal to I k times psi. Therefore, del squared psi is equal to del dot del psi, which is equal to I k dot del psi, which is equal to I k dot I k psi, which is equal to minus k squared psi. Therefore, the eigenvalue of del squared is minus k squared, and the Schrödinger equation becomes h psi is equal to h cross squared k squared by 2m times psi, which is equal to E psi. That is, the eigenvalue or the energy, eigenvalue of the Hamiltonian or the energy E is equal to h cross squared k squared by 2m. Okay. So we have shown that the energy eigenvalues for a free particle are given by E equals h cross squared k squared by 2m. Note that the wave vector k can take on any value, any direction and any magnitude. We have not placed any restriction upon the direction of propagation of the wave or its momentum. In other words, the energy eigenvalues of a free particle are continuous and not quantized. They can take on a continuum of values. Now consider a particle that is confined in a one-dimensional box of length L with infinite walls. So the particle is free inside the box, that is V equal to 0 inside the box, but it has infinite walls, infinite potential outside the box, and therefore there is no probability of the particle going outside the box. So V equal to 0 inside the box, that is for x between 0 and L, and V equal to infinity outside the box. So as before, h psi equal to E psi with h equal to t plus v, and t equal to half p squared by m, which is equal to minus h cross squared by 2m d squared by dx squared. The difference now, however, is that we have to solve the Schrodinger equation subject to certain boundary conditions. The condition is that because of the infinite potential outside the box, there is no probability of finding the particle outside the box. The infinite potential causes the wave function of the particle to vanish outside the box and at the boundaries. Note that psi squared or modulus of psi squared is the probability. So the psi has to be equal to 0 at x equal to 0, and psi has to be equal to 0 at x equal to L. These are the boundary conditions that we need to impose to solve the Schrodinger equation. So let us now solve the Schrodinger equation. H psi equals minus h cross squared by 2m d squared psi by dx squared equal to E psi, subject to the boundary conditions that psi equal to 0 at x equal to 0 and at x equal to L. As before, we write psi in the wave form. Psi equals a cos kx plus b sin kx. Now if we put x equal to 0, we find that the second term vanishes, whereas the first term doesn't. In other words, the boundary condition psi equal to 0 at x equal to 0 is satisfied only by the sine term, and therefore we had to put a equal to 0 in order to make the first term vanish. Thus we put a equal to 0, and to satisfy the second boundary condition, we put k equal to n pi by L, where n is an integer. Then we see that the second boundary condition, that is psi equal to 0 at x equal to L, is also satisfied because sine n pi is equal to 0. Thus we get psi equals b sine n pi x by L, where b is determined by the normalization condition to be b equal to square root of 2 by L, as we will now show. To determine the normalization constant, we start with the form psi equals b sine n pi x by L. Normalization requires that integral psi star psi dx is equal to 1, but since this form of the wave function is real, this means that integral psi squared dx is equal to 1, or in other words, b squared times integral 0 till L sine squared n pi x by L dx is equal to 1. The limits of the integration are the size of the box, since the particle cannot go outside the box. Note that sine squared n pi x by L is equal to half into 1 minus cos 2 n pi x by L. So 1 is equal to half b squared times integral 0 till L 1 minus cos 2 n pi x by L dx, which is equal to half b squared integral 0 till L dx plus b squared L by 4 n pi times sine 2 n pi x by L from 0 till L, which is equal to half b squared times x from 0 till L plus b squared L by 4 n pi into sine 2 n pi minus sine 0. The last two terms are 0, and therefore this gives 1 is equal to half b squared L, or b is equal to root 2 by L. We have thus solved the Schrodinger equation h psi equals minus h cross squared by 2m times d squared psi by dx squared equals E psi for a particle in a one-dimensional box subject to the boundary conditions, and obtained the solution psi equals root 2 by L, that is a normalization constant, times sine n pi x by L. Putting this form of psi into the Schrodinger equation, we get h psi equals minus h cross squared by 2m times root 2 by L times d squared by dx squared of sine n pi x by L, which is equal to minus h cross squared by 2m times root 2 by L times n pi by L times d dx of cos n pi x by L, which is equal to h cross squared by 2m times root 2 by L times n pi by L whole squared times sine n pi x by L. But root 2 by L times sine n pi x by L is just psi. So h psi is equal to h cross squared by 2m times n pi by L whole squared times psi, which is equal to E psi. Or in other words, the energy eigenvalue E is equal to n squared pi squared h cross squared by 2ml squared. But since h cross is equal to h by 2 pi, this is E equals n squared h squared by 8ml squared, where n is an integer. In other words, the energy eigenvalues are quantized because E can only take the values n squared h squared by 8ml squared, where n is an integer. For n equal to 1, we obtain the wave function sine pi x by L. For n equal to 2, we get sine 2 pi x by L. For n equal to 3, the wave function is sine 3 pi x by L. For n equal to 4, sine 4 pi x by L, and so forth. So, this clarifies the origin of quantization. The free particle, for the free particle, the energy is not quantized, whereas for the particle in a box, the energy is quantized. So, in other words, quantization is a consequence of the boundary conditions we have to impose upon the wave function. So, the mysterious quantization that Planck introduced, we see that it turns out to be a simple consequence of the wave nature of the particle and the boundary conditions that have to be imposed upon the solutions of this wave equation.